So welcome back at 2-7. We're going to look at inverse variation models. In fact, this is our very last style. This is our last one. So we can be sad because we are going to, the next thing we're going to look at is how to choose the best model. And then we're going to give you a project on this stuff. So we're going to use inverse variation functions as models in various situations. So in this warm-up situation, we have 6 pounds of ground beef. We're going to make into hamburger patties. So we're going to complete the table of values that relate the weight of each patty to the number of patties you make, then make the scatter plot of data. There we go. So as we take this, if I just buy make one patty, that's a 6-pound burger. So essentially all I'm doing is taking the 6 and dividing by the x value, right? Essentially I'm just doing 6 and dividing it by the x value to get each one of these. And of course it goes on. If I made 100 patties, I would have very, very small patties, but I would still have patties in existence. So now how to graph this, we need x and y on the coordinates. So I'm going to put the number of patties on the x here. And then over here, I'm going to say the weight per patty. So now that I have a scale, I'm counting by ones on each one. So over here, goes all the way up to 10 patties, but clearly I'm going to extend farther. And then the highest it goes is 6 pounds. So if I make 1, it's a 6. If I make 2, it's a 3. If I make 3, it's going to be a 2. And 4, I don't have a 4 there, but I do have a 5, which is at 1.2. And then 10 at 0.6, like so. So in this situation, no S there, the weight per patties varies, and here's a new vocabulary word, inversely. Inversely. Or is inversely proportional. There are two ways to say it. Inversely proportional to the number of patties. The domain is just the whole numbers. Is the set of whole numbers. If you wanted to say, but Swenson, according to my graph, if I connect the dots, it's just greater than 0. Okay, you could argue that too. But practically speaking, we're just counting by ones. So we're going to stick with the whole numbers. And what about the range? Well, the range is the highest it goes, in my context, the highest it gets is 6. And the lowest it gets is, it can keep going on forever. So it looks like my range is between 0 and 6. Notice that it never gets to 0, but it does get to 6. So I have a less than, but then a less than or equal to for the second part there. So we're going to look at some characteristics of inverse variation and see how it compares to the other stuff here. So inverse variation. It can be said that y varies inversely as x, or y is inversely proportional to x. Whenever this occurs, that y is k equals k over x. So notice that in this case, I'm dividing, like in the sense of the patties. I had 6 pounds, and I divided by the number of patties there. So I do have a constant, a variable, and the constant. Good, so make that change real quick. This is the constant of variation, is k. So in our original situation, I have 6 pounds of meat, and that doesn't change. It's constant. So with this model, the domain is always going to be all real numbers except 0. It's going to be all real numbers except 0. Practically speaking, we don't always include all real numbers, like in our previous situation. We only included the whole numbers because we are counting by patties. Okay, next, the range. Turns out the range is going to be all real numbers as well, except 0. Clearly put, notice here, I cannot legally divide by 0. So if x were 0, it would be undefined. So that's from the equation, that's where I'm getting that. From the graph, you'll see in just a second. So here's what the graph looks like when k is greater than 0. When k is greater than 0, you're going to have a situation that looks pretty much like we had up there, where we're bounded in just quadrant number 1, but technically it's also going to go this way here, and it's going to be bounded in quadrant 3. Again, this is quadrant 1, and this is quadrant 3. So if k is less than 0, effectively I'm throwing a negative there in front of the parent function, which means that I'm going to do a vertical reflection. So what was originally in quadrant 1, this one here, is going to reflect into quadrant 4, like that. And the same holds true. The quadrant 3 is going to reflect to quadrant 2 there. So here are the basic functions, what they look like when we have something that's inversely proportional. The shape of the graph has a name. It's called a hyperbola. Each one is, together it's a hyperbola. Together. So both of them combined. They have asymptotes at x equals 0 and at y equals 0. In other words, the axes, both the axes are my asymptotes. So, given that we have the average song size, we're going to plug all of this into L1 and L2 in just a moment. But we're going to find a formula that gives the average number song n that will fit on an MP3 player as a function of the average song size. So, S, we're going to use this as something called a typical point. This is just a typical point. Notice it says in quotation marks typical, because we honestly don't know which one of these is the most typical, which one looks like the one it should be. And the answer is you don't really know. You just pick one, okay? I think the tendency is to pick one in the middle, like don't pick an extreme, like the smallest or the biggest. Pick one somewhere in the middle. So in this case, it's given to us. So how do we find k? Well, if I have my basic function, which is this, y equals k over x. How do I get k by itself? What do I need to multiply by? X on both sides. So k is just x times y. That's it. K is x times y. In our context, it's 4.2 times 7,600. And that's going to give me what k might be. So, because our calculator does not have a function for inverse reg, we are just going to manually calculate it. Now that I have my constant of variation, I'm going to graph it. So when I graph my data, after entering into L1, L2, I get this. And then I enter in my formula into Y1 and overlays, and it seems that it works out pretty well. Notice that my curve fits pretty well. Notice that this one's a little bit off, but all the other ones are relatively close. So it seems to be a pretty decent fit for my data. So I'm going to want to, besides just looking at it, want to evaluate to see if it is a good fit. I forgot to put that back in here to get my super secret equation. So my super secret equation looks like this, 31,920 divided by x. So that's my function that I'm going to say is like my inverse regression. Next, we're going to use residuals to see how far off. Remember what residuals are? It's the observed minus the expected. Observed minus the expected. So what we're going to do is based on L2, that's the what it says is my observed. And then the expected is going to be from my from my function right here, y2 minus L1. So excuse me, y1. So I'm going to take the function that I just entered in, and L1 is my list, and we're going to see here, when we enter that in, what my residuals will be. So what does that say about what does the residuals tell us? Well, the residuals tell us that because we have a bunch of stuff that's above, so 200 is above, we're off by 200 songs. This, the data is, excuse me, the observed is above my expected by 200. And then one of them is below my expected by almost 900 songs. But this one off by 14. This one is 0 because that's the number we used. This was my established number. So we've got some that are above, some that are below. And because only this one is a huge issue compared to 8,000, we say it's about 10% off, 10% off. But these ones here are so low relative to the expected value or the observed value that we see that the residual ends up being a really good indicator that this model is pretty good. The model is pretty good. So use the residuals to assess the quality of your model. And so a quick observation would be because residuals, let me learn to spell there. Are plus and minus and relatively small, except for the one. Our model is pretty good. Now, the problem is I don't know if it's the best. So what if I chose to find K in a different way? If I said instead of using the 4.2 and the 67600, what if I used the 4.1 and the 78? Well, what would my residuals be different? Well, they might be different, but again, that's a lot more work to determine. So we don't know if this is the best, but we do know it's a pretty good model. And of course, we can see that visually, because as we look at this here, we see that the only real one proportionally that's off is this guy right here is off, but all the other ones are relatively close. So about 10,000 songs averages to what? Well, that's a pretty straightforward. All we have to do is put 10,000 into my formula, which would be 31,920 divided by x. So if I take the reciprocal of both sides, or multiply by x, some of us probably prefer that method. So multiply both sides by x, and then divide by 10,000, and then divide by 10,000. I get x is equal to 31,920 divided by 10,000. 3.192 megabytes per song is about what we expect. And we can look at the trace to do that one as well. All right, the last thing we want to look at is something called the inverse square relationship. So let's look at this. In our physical world, y equals k over x squared is a common relationship. So for example, the intensity of light hitting an object is proportional to the inverse square of the distance between the light source and the object. In other words, the farther away you get, not only does the intensity of the light diminish, but it diminishes by square. We square the distance as it moves away. So it diminishes quite a bit. Next, same applies to radiation. As radiation is hitting as an object is proportional to the inverse square of the distance between the source and the object. So obviously getting yourself away from radiation has benefits because the radiation won't affect you as much the farther away you are. Sound is the same way. Distance related to the intensity of the sound, usually measured in decibels. All right, so we've seen these four situations where we have light Radiation, sound, and gravitational force, all related to distance squared there. So let's look at this one. The intensity of light from a point source is inversely proportional to the square of the distance of the light source. Again, sounds complicated, but there's only 3 things to write down. Suppose that at a distance of 5 centimeters, the light intensity is rated at 600 lux. What would be the intensity of a distance, of an object of distance? Let's try that again. What will the intensity be at a distance of 10 centimeters? And then we want to check at 23 centimeters. Well, remember our basic function is this one. Y equals my constant of variation divided by x squared. And in this case, my x is distance. So if we're talking intensity, I don't know what letter we might use here, but they might use the letter I for intensity. So let's go ahead and do that, I for intensity. We don't know what K is yet. Well, we don't know what D is either. So we're going to use, instead of X, we're going to use D for distance, and we'll say that's squared. So we only have 3 things, the I, D, and the K. So in this case, I'm going to use the given information, the 5 and the 600, in order to find K. Once we find K, we can plug it back in. So I, the intensity, is 600. So let's put that there, 600. Equals my unknown K right now, and the distance says 5 centimeters, and I do have to square that. Now again, to get K by itself, I just have to multiply both sides by 25, which is 5 squared. And now I have my value of K. So K is equal to... Now that we have that, we can write our super secret function. It looks like this. The intensity of light is equal to 15,000 divided by whatever the distance is squared. Okay, so now we just have two things to solve for. Notice that we say, oh, look, we double the distance, so shouldn't we cut this one in half? And the answer is, well, only if it were directly proportional, but it's going to be significantly less. It's not just 600. We're going to cut that in half to be 300. It's going to drop by quite a bit. So let's go ahead and plug that in. So I is equal to 15,000 divided by 10 squared. Divided by 100. 2 zeros drop out. And I'm left with 150 lux. So after we plug 23 in here, we get 23 squared. We end up with about 28.4 lux, or lumens. The next one here is the force exerted by the electrical field between 2 charged objects is inversely proportional to the square of the distance between them. At a distance of 1.5 meters, you measure a force of 30 newtons. What will be the force at a distance of 3 meters and at 15 meters? And these are the results that I got. K was 67.5, and then how much force is exerted when we're 3 meters away? That's 7.5 newtons, and how about 15 meters away? 0.3 newtons.